molecular formula sometimes. So remember how that works, okay? But now here's the deal. So remember, molecular formulas here, and sometimes you can divide each of the subscripts by a whole number and get another set of whole numbers to get a reduced empirical formula. Then we actually did some problems where you went from weight percent to the empirical, the simple formula. Well, now we're going to see one last sort of problem where you can actually go from percent data to the simple empirical formula. And if you have one more piece of information, you can backtrack all the way to the molecular formula of that compound. So that's where we're going with this. So the missing piece, and we're going to do only one problem, the missing piece is you need to know for that compound of interest, you have the percent composition, you can get to the simple empirical formula, you need to know the weight, the molecular weight, okay? Then if you know that, you can go ahead and get to the molecular formula. So here's an example we actually did the other day. This is Wednesday, must have been Monday. So where we had these weight percents, and remember I had a table over here, and I had the elements, and I took those masses and took those percentages and said they were the grams based on a 100-gram sample. And then I came up with the relative moles. I had a few columns. I divided by the fewest moles, all that. And maybe we had a cleanup step, multiply by 2 or 3 if need be. And we came up with empirical formula C2H5O. All right, so for the same compound, now if they give you this extra bit of information like they have, we can take that empirical formula C2H5O and find out what the real molecular formula is if they give us the molar mass. So the molar mass of this compound is 90.1 grams per mole. And some of you guys might be kind of thinking how that, maybe already thinking how we do it. So what this is trying to tell you is that empirical formula is kind of a repeating unit, like a base unit. We could have it times 2, so it'd be C4H10O2. We could have the whole thing times 3, it'd be what, C6H15O3. We can have it scaled up times 4, that'd give you what, C8H20O4. Those are all possibilities, okay? So what we're gonna do is, if we recognize that the molar mass of the whole compound is equal to some whole number of these little repeating units. Kind of keep that in mind. If you rearrange that actually then, we can get to how many repeating units we have if we simply take the molar mass of the whole compound divided by the molar mass of the empirical formula. It's easier to show you than we call this. So the molar mass of the empirical unit, or excuse me, the empirical formula, the repeating unit that we're going to have looks like this. So we take 2 times 12.01. You guys writing this down? Plus 5 times 1.008. This is the empirical formula. This is the base formula. Plus 1 times 16.00. And sometimes people say, do you need the 1? No, but it makes me feel better. So the repeating unit we have, sort of the base unit is 45-ish. And the big one's 90. So what do you think? I'm thinking we need 2 of these units. Okay. So this is what that looks like. So 90.1 was the overall mass of the molecular weight. Okay. And then we just came up with repeating unit 45.06. So you're looking at 2. So we need to scale the C2H5O up.
So we're talking about 2 molecules? I've got
2 of these repeating units to make it 1 molecule. So based upon that, I could say scale it up and know that for the real molecular formula must be C4H10O2. So that's how you do that sort of thing. It's interesting in chemistry problems, how sometimes this approach kind of repeats itself too. Okay. So this set of homework is going to be due tomorrow.
Can you go back to that next slide and get out?
I can. You're fine. So tomorrow's lab, which lab number are we doing?
7.
7. Music 20 years. I almost at the last minute thought maybe we should switch it up and go 5, because 7 actually, we won't have gotten it to it in lecture yet a little bit, but I think I'll do fine with pre-lab, and we'll get to the calculations, the nuts and bolts of the calculations on Friday. So, all right. So like I said, we're skipping, I thought I fixed that. We're skipping 4 for now, going on to 5. 5 looks like this. So we've already, I feel like we've already kind of talked about this a little bit. Like, I'm not a wordy person, so I really like the idea of chemical equations to describe chemical reactions. So, like, we talked about a chemical reaction, though. You know that a chemical reaction has occurred if you've got new substances. Here in a minute, I'm going to show you, well, how do you know new substances are formed? Well, we'll talk about that. Okay. But we're not going to do any nuclear chemistry in here. That's to say that nothing is going to transition from one element to another element. Okay. So we're going to work with this conservation sort of approach, where all the elements, and the way I do this is what you start with, and this is what you end with. So all of the atoms are what you start with, elements and all that, you're going to end with. It's a conservation property. The nuclei remain unchanged. So I mentioned, how do you know new substances are formed? So what they didn't show you is basically probably 2 clear liquids put together, and you get something that's not clear anymore. This actually, we'll be talking more about this in Chem 2. This actually is a lead-2 iodine precipitate. This is showing you 2 clear liquids. So we have a liquid in the pipette. We have a liquid here. When the 2 come in contact, again, new substances are formed. You can't always see them, but these are examples of you being able to see them. Okay. This is what you're going to do, not this Thursday, but next Thursday. Of course, we can't destroy currency like this, but you will be taking copper wire, and one of your first steps of chemical reaction will be to dissolve the copper wire. But it's more than just dissolving, it's a chemical reaction. I don't know if you guys can see kind of the green around it, and if I were to animate it, that brown haze is actually nitrous oxide fumes, so we'll be doing this in the hood. Okay, so new substances are formed when a chemical reaction occurs. New substances are formed when a chemical reaction occurs. So there are endothermic and exothermic reactions. Exothermic reactions release heat, endothermic reactions take in heat. Now, just because something releases heat doesn't mean it's a chemical reaction, but this is a chemical reaction. Okay, so chemical reactions, new substances are formed. And I've already mentioned, I really like this shorthand notation we do with chemical equations to describe the chemical reactions. So just like we read a sentence from left to right, we also read a chemical equation from left to right. Terms you want to be familiar with is what you start with is called your reactant, what you end with is called your product. And we will be probably again, like in Chem 2, looking at reactions that actually go from left to right like this, but they also go from right back to left. So they're 2-way reactions. So we use an equation to describe a chemical reaction. And I'm going to kind of break up 2 broad types of equations. There are equations that aren't balanced for mass. They aren't balanced for the same number of atoms that you start with and end with. And then there are the balanced ones. Okay? So it's a minor distinction. So I'm going to start with the unbalanced ones. And again, this is stuff that you're probably already familiar with. What an unbalanced chemical equation describing a chemical reaction will show you is what you start with and what you end with. And we're not going to use words, we're going to use the chemical formulas. Thank goodness. Okay? They may or may not show the physical phases, and you've seen, I have a list here like S is for solid, L is for liquid, A is for AQ, G is for gas. Also, really concisely, your unbalanced equation may or may not show anything kind of you as the reader need to know right away in order to make this reaction occur. Oftentimes it's written over the reaction arrow, something nice and concise. So these are like the little abbreviations you might see next to a reactant or product. These abbreviations will be in parentheses and they will be to the right of the species, the reactant or the product that we're talking about. If you see AQ, that means dissolved in water. So like if you saw, for instance, NaCl, that's supposed to be Cl, AQ, you just have to picture that is running around, and we'll talk more about ions, but N is Na plus ions and Cl minus ions. So Na, this is my water, my beaker water, Na plus, Cl minus, you get the idea. Okay, so that's what AQ means. So I mentioned kind of if the person who is familiar with the chemical reaction, if they want to put something over the reaction arrow, right quick to tell the reader what needs to be in place in order for reactants to proceed to form products, they can do that. If there's a minimum heat, if there's a specific temperature, if they need to have a catalyst go from left to right, from reactants to products, if it needs to be in the dark, that sort of thing. Okay. So 2 words that start with the letter Q, and I hate words that start with the same letter, but we have qualitative and quantitative. So qualitative is talking about the quality of something. So what do you think quantitative is talking about?
How much?
The amount, how much, exactly. Exactly. So qualitative is just kind of more bird's eye view. Quantitative is how much. So all the things, the aspects of a chemical equation that we talked about just a minute ago involve in qualitative things. What's the reaction? What's the product? Are there any, well, I guess if you give a temperature, specific temperature, that'd be quantitative. So unbalanced chemical equations give qualitative information. They don't give quantitative information. So yes, at the end of, and I'm just looking through this, so slow me down if I'm going too fast, but at the end of this part, part 5, you guys are going to apply a process where you take unbalanced equations and balance them. So what's the good thing about a balanced equation? Well, it adds that element of quantitative, okay? It fixes that part of it. But a balanced chemical equation will have all the same potentially qualitative information that you saw a minute ago, and it will give you quantitative information. Up here, kind of when I hold my hands up, I'm talking reactants over here in this hand, products over here in this hand. If you balance it, you not only have the same types of elements in your reactant and product, okay, but you have the same number of atoms in the product side. So if you balance it, you get qualitative and quantitative. Okay. So I've got some pictures here to kind of show you pictorially what that looks like. On either side of the reaction arrow, you have the same number of atoms of each type of element. Here's one. And I kind of talk about it, I call it a brick wall. So here's my reaction arrow right here. And so I actually, here's my reaction arrow here. I make a brick wall where on this side I have the reactants, and on this side I have the products. I teach Introduction to General Chemistry. And so it's a step, it's like you get in high school basically, Chem 1, 2, 2. And actually on their test for this, I asked them, like, look at that and tell me which are reactants and which are products. Don't you wish you were taking Chem 1, 2, 3?
Yes.
Yeah. I'm offering it next spring, or next semester. So. But if you, but I kind of say that, but a lot of times Chem 1, 2, 2 won't transfer, definitely won't transfer the same as 165.
Mm-hmm.
So. Okay, so look at the little red balls, and here's, by the way, down here is this is balanced now. Now you see a number 2. This 2 goes with the fact that there are 2 of those. What's the number here in front of the O2?
1.
1, very good. And there's just 1 of these. And this 2 goes with the fact that there are 2 of these. Yep. I'll write it up on the board. Where I have the 2 and you told me 1 in front of the O2 and a 2 in front of the NO2, that is called, I think it's German, a stoichiometric coefficient. I abbreviate it affectionately stoichcov. Okay, stoichiometric coefficient. And we'll talk about kind of how you get that 2, 1, and 2, respectively. But that's balanced. Here's another one that's balanced. Again, with the brick wall at the reaction arrow. And here we have methane represented here. 2 molecules of O2 represented here. 1 molecule of CO2. 2 molecules of H2O. So if we count the black, I got 1 black ball on both sides, that's my carbon. Looks like I got 4 white balls, those are my hydrogens, and I got 4 red balls, which are my carbons. You guys okay with that?
No. You went a little fast.
Okay. So there's a 2 here that represents 2 of these molecules. And there's,
so we're not counting, like, I see 4 of those.
so there are 4 individual atoms,
Yeah.
but they come in pairs.
Okay.
Yep. Yeah, so O2 is one of those elements that always likes to have a buddy. It's a diatonic element. So they come in pairs. So you can't have just an O. And you'll have an O2. And kind of to your point, the way I think of it is I need 4, and we'll talk about how we kind of go back and forth, but I have 4 red carbon atoms here, and I have 4 red carbon atoms over here, albeit they're, oxygen. I meant oxygen. 4 red oxygen atoms there, 4 red oxygen atoms here. These 2 oxygens are associated with my CO2, and these 2 oxygens are the atoms that make my water. Better?
Yeah.
Better? Okay, good. Because we are gonna talk about, and I talk about how you balance equations. So I usually put like a little squiggly mark there. So what number is in front of the CH4? 1, yep. And sometimes I'll even write that 1. I put a squiggly mark there. Of course, that's a coefficient, stoichiometric coefficient of 2. And what's this one? It's also 1, yep. And this one's 2. So, yep. So these are already balanced for you, and we'll talk about how you get those without seeing the balls, the different colors. Okay, so here's a couple little videos. Side, I'll put P for phosphorus. I'll put Cl for chlorines, and it's like a little tally. Over on the product side, P for phosphorus, Cl for chlorine. And since this one's already balanced, what I'm just going to do is go back and kind of tally. So I only have phosphoruses here with this P4. So how many phosphorus atoms do I have if I have 1 P4?
4.
I have 4, yep. So here I've got 6 sets of Cl2. So if I break those Cl2s up, individual chlorine atoms, how many chlorine atoms do I have? I have 12. You buy that? So if it's balanced, I should have 4 phosphoruses and 12 chlorines on the other side. So in this case, I have 4 units of PCl3. So if I break it up into individual atoms, how many phosphorus atoms do I have? I have 4 phosphorus atoms, and how many chlorine atoms do I have? 12, yep. So that's just a verification that it is balanced, and it smiles all the way around. Okay, so that's kind of what we're going to see. This is the same reaction we saw in still images. Yeah, very exothermic, a lot of heat evolved. Okay, so let's make a brick wall here. And I have magnesiums is equal to oxygens equal to magnesiums equal to oxygens equal to. There's a lot of stalling in working chemistry problems if you do it right. So how many magnesiums do I have on the reactant side? 2. Yep. And how many oxygen atoms do I have on the reactant side? 2. Very good. On the product side, if I have 2 of these units, which is 1 magnesium, 1 oxygen, how many magnesiums do I have?
2.
I have 2 magnesiums. How many oxygens do I have? 2. Yep, there are 4 atoms, but that's how they're divvied up. So yeah, it's balanced. Conservation of matter. Okay. That's awesome. So, as long as you're not doing any sort of nuclear chemistry, like some sort of nuclear fission or fusion, you should have the same matter you start with should be represented in the matter that you end with. Not specifically just any matter, but the specific atoms, okay, like we talked about. So we're going to do a problem here, and a few things. Thou shalt not play mad chemist. Thou shalt not change any of the subscripts, because if you're changing the subscripts, that's what we use to describe what the chemicals are. Okay, so like if you were working with, for instance, if I wanted to look at H2O, and I know it breaks down into hydrogen and oxygen, okay? And actually I could put a little L here for liquid, a little G here for gaseous hydrogen, a little G here for gaseous oxygen. I can't go and say, I can balance that if I change this oxygen over here on the product side, if I change that to a 1. Like, how hard is that? No, because you have changed, you basically, when we talked about diatomic elements, you basically said that that oxygen is going to be running around in some sort of radical or something. No. We'll talk about kind of going back and forth, but I cannot do that. As some of you guys know, if I go ahead and put a 2 here, I could put a 2 here and leave this as a 1. See, it's magic. And actually, that did it for me. And we're going to talk about where the squiggles are. Those are my stoichiometric coefficients.
I'm still confused how you're getting the
balance?
kind of like how to put each element into like what spot, and
So someone is, I don't know if this is your question or not, but somebody will tell you what species, what things react, and what things form. Somebody will give that for you. That's like the unbalanced equation. And then what you need to do is put that coefficient, that big number to the left of the species to say how much of each there is. Was that your question?
Yeah, I'm just kind of getting confused on how, like, are we gonna have are you gonna give us like a reactants, and then do we have to come up with the product?
No.
And have to label it? Or?
Nope. I will give you, and we're gonna look, I guess, just like a couple of examples.
Okay.
And I will give you the species, I call them the species, the reactants and the products.
Okay, so we'll have all that information.
Yeah. For this course you will, yeah.
Okay.
Yeah. Good question. Yep. Okay. What else? Okay, so you can't change the subscripts, but you can, and you are encouraged to change where I put the squiggle marks there. The squiggle marks are to the left of the species, to the left of the species, to the left of the species. Those are called stoichiometric coefficients. They're big, okay? And they just mean relative numbers that you have of that reactant or product. You can't do that. It's not up here, I usually say I would use a pencil, because you're going to see I go back and forth. So sometimes during the process of balancing an equation, given the reactants and products, I'll like put a number there. I'm like, wait a minute, no, that doesn't work. And I'll erase it and put a different number there. Okay. So as we were kind of checking if something was balanced, keep in mind that that big number to the left of the species. That stoichiometric coefficient applies to everything in the formula. Okay. We kind of did that when we tallied up atoms. All right. So let's do this one. And so if you grab your sheets, girls and guys. Okay. So I do squiggly mark. I'm going to account for elements of Fe, H, and O. Fe, H, and O. And the way I start out is there's one across, they are ones. My stoichiometric coefficients are ones across the board. So how many Fe's do I have over here? 1. How many H's do I have over here? 2. How many O's do I have? 1. Cool. How many Fe's do I have on the product side? 3 H's, 2 O's, 4. Awesome. Time for a cup of coffee. So I guess I don't, I thought I said it in my slides. Maybe I say it coming up. I'll put a star next to the one that is in its, my words call it uncombined elemental form. So do you see anything up there that's not combined with anything else? Fe. I'm going to put a star next to my Fe, and I'm going to hold it till last. And honestly, as it turns out, my H2 is also not combined with anything in its elemental form. Okay. So I'll put my squiggly marks here. The squiggly marks are tell me, it's a convention I came up with where I need to put stuff. So I'm not going to put, it'd be tempting. I'm like, oh, why don't I just put a 3 in front of the Fe? Well, you hold it till last. Okay. So let's go ahead and work with our H2O and our Fe3O4. Clearly, I have 4 over here on the product side. How can I get 4 oxygens on the reactant side? 4. Yep, I'm just going to put a 4 in front of the H2O. Now, when I change my coefficient, I have to update. So now with a 4 in front of the H2O, how many H's do I have? I'm like an 8. Yep, I have 8. Yep. Oops, I wrote 6. I have 8. And when a 4 there, how many oxygens do I have? 4. Sorry, this is kind of messy, but yeah. So now my oxygens work. And actually in this process, it's called trial and error by inspection to balance an equation. And sometimes you have to go back and revisit what you put, fix it. Okay, well, let's tackle, and there would be different ways to approach this, but I'm liking my hydrogens. Let's fix hydrogens. What do I need to do? Yep, I hear people say put a 4 in front of the H2. Yep, so if I put a 4 there, now I need to update my H's. How many H's do I have?
8.
Yep, now I have 8 H's. Yep. Wow, so these actually, right now, my H's are balanced, my oxygens are balanced. So now what I need to do with my Fe's? Yep, put a 3 here. Yeah, but do you see where it's not, when I say linear, it's not like from left to right, it's kind of back and forth, and you pick what you want to balance. And actually, before we leave, I'll show you online, if you just Google, so this will help you with your Alta homework, but if you just Google balance equation calculator, there's a lot of them out there. And every once in a while, I'll hit a hard one, and be like, wow. Can't use them on the test.
So on those, you said to use the ones that are separate last, and then do the product side first or the reactant side?
It varies. It kind of depends. If you take a bird's eye view, it kind of depends. And people could start at different places and end up with the same result, quite honestly.
Okay.
But yeah, it depends. I like to take the most complicated one and then go from there. So yep, it is balanced. And then my sheet here kind of tallies them up. That is balanced. Okay, So this one, we'll be talking more about ions. Sodium chloride, I showed you a minute ago, in aqueous solution gives you Na pluses and Cl minuses. But for now, you probably, how do I say this? You may have heard that that this thing right here, SO4, anybody know the name of that? Starts with letter S. Sulfate. It is sulfate, exactly. And it stays an entity. Here's one for you. Anybody know what OH minus is? Hydroxide. Yeah, and it stays an entity. So honestly, we could go ahead and split up aluminum, sulfurs, oxygens, sodiums, and hydrogens. But I'm going to keep the SO4 as an entity, and I'm going to keep the OH as an entity. So we get to the same place either way. So if I'm counting things, I'm going to say my AL is equal to my SO4. Actually, it's a 2 minus, but we'll leave it. SO4 is equal to. And my NAs is equal to, and my OH is equal to. So the thing that's different about this problem is I'm leaving SO4. I see SO4 here. I see SO4 here. I see OH here. I see OH there. I'm leaving it as an entity. So I'm going to put on the reactant side and the product side. Product side, I need to account for ALs, SO4s, NAs, and OHs. Okay, so with that in mind, on the reactant side, how many ALs do I have? 2. How many SO4s do I have? 3. I have 3 SO4s. How many NAs do I have? Just 1. And how many OHs do I have? Just 1. Perfect. On the product side, how many ALs do I have? Just 1. Yep, because this 3 only applies to the OHs. Yep, we just have 1 AL. How many SO4s do I have? Over here, how many SO4s do I have? Not 3. Yep, I just have 1. Yep, just 1 SO4 because there's like a 1 in front of it right now. Yep. How many NAs do I have? 2. And how many OHs do I have? 3. I don't have anything to kind of wait till last. So let's just jump right in there. How can I fix my SO4s? Yep, change that 1 to a 3. Yep. Again, you can start different places. If I change this to a 3, I have to update my NAs. How many NAs do I have now?
6.
Yep, I'm liking 6. And now how many SO4s do I have? I have 3, which is what I wanted. Okay. Wait a minute. Drat, what did I do here? Sorry, that's still a 1. That's a 3. There, I'm liking that. Wow, let's fix our NAs. That's crazy. So how can I fix our NAs? Yep. I'm going to put 6 over here. I'm going to update. So that did give me 6 A and NAs. How many OHs do I have? 6. Do you see where the whole back and forth comes? And this is a 1. This one's a 1 still. So how can I fix my OHs? I heard a 2 over here. If I put a 2 here, that will give me 6 OHs. Yeah. Oh, that will also, I heard, fix my ALs. I agree. So if I 2 there and update my ALs, now how many ALs do I have? 2. And how many OHs do I have? 6. Now, to me, I got OHs, NAs, SO4s, and ALs. So we did it. Usually when I do this, I start at a different place, and then I have to go back and fix it. Okay. You might be wondering, well, how would I know SO4 and how do I know OH? Well, you will know when we get to that in Chem 1. But for now, I just want to point it out. Okay. Ta-da-da-da. And it works. So this was the thing where I said save the Fe or the H2 till last. If one substance is in its elemental, uncombined, not stuck with anything else, go ahead and leave it till last. It just helps. So let's do one more. Best to last. So I make a brick wall. I need to account for carbons, hydrogens, and oxygens. Carbons, hydrogens, and oxygens. So how many carbons do I have on the reactant side? 4 hydrogens, 10 oxygens, 2 carbons on the product side, 1 hydrogens, 2. Now for oxygens, make sure you count. Yeah, I heard 3. We have to, and this is where it makes life a little interesting. 3. Because as we change the coefficient of either the carbon dioxide and or the water, we're going to mess up our oxygen. Okay, so I'm going to put a little asterisk here. I'm going to leave that one. I'll put little squiggly marks where I can change the stoichiometric coefficients. For something like this, I usually start with my carbons. So how can I fix my carbons? Yep, put a 4 in front of the CO2, and now we update. So that gave me 4 carbons, and now how many oxygens do I have? Yep, I'm like a 9 because I have 2 oxygens here, and I have 4. Yeah, I have 8 oxygens here in the CO2 and 1 oxygen there in the H2O. So that goes to a 9. All right, so let's go ahead and fix our hydrogens. What do you think? Yep, put a 5. See, it just depends on how it is where I put what. But yeah, I'm going to put a 5 in front of my H2O and update. So I put a 5 here. Now how many hydrogens do I have? 10, which is perfect. And then how many oxygens do I have? Get out your calculator. So we have 5 plus 8, yeah, 13. I'm liking 13. So this is a classic. You hate that term. So this is a classic where my carbons, my hydrogens are great, and it's got an oddsies, evensies problem going on. Because if I were to ask you, how do you fix my oxygens, our oxygens, you'd be like, well, they come in pairs, and I need an odd number. Yeah. Now I'm going to show you a couple different ways to do it, okay? So, and I have a slide to say why this is okay, but if you think of, how do I say this? So diatomic elements like oxygen are stuck in pairs. So there's my O2 molecule. There's my O2 molecule, okay? If I were able to break that chemical bond between those oxygen atoms that makes it an O2 molecule, how do I say this? So how many oxygen atoms would I have in one molecule? 2. Yeah, I got 2 there. I could do it again and do it again. Oops, sorry. And I'm on my way to what, 13? Wow. Okay, so you get the idea. If I were to, I'm going to actually go with 13 halves O2 molecules. I need 13, and if I break them in half, and I take 13 of those halves, that gets me there. You'd be like, is that legit? And yeah, it is. It's kind of cheating. And the only reason I can do that, 13 halves O2s, is because, how do I say this? If I take a half of a molecule, I mean, it's all symmetrical, and I'm getting to my individual atom, which is what I want to get to. Well, if you buy that, so let's update how many oxygen atoms I have now. 13, yeah. So I've done it. I've done it. If you buy that, and I'm telling you, that is legit. Yes, ma'am.
So you cannot write 6.5.
You can write 6.5. It's the same dip. Yep, 6.5. Must be a European thing, but no. Yes, you can.
Sweet.
Yes. Okay.
Oh boy.
So now, if you're like me and you don't like halvesies, you can scale things. Okay? So I could actually It's like, these are like recipes. I think of your reactants as your ingredients, and your product is like the yummy thing you make in the kitchen. So we do this all the time in the kitchen. If I want to double a recipe, what would I do? I would take this times 2, this times 2, this times 2, this times 2. I doubled the recipe. What did that mean? I got twice as much reactants, twice as much ingredients. It gave me twice as much yummy stuff. I call it scaling, okay? These are 2 perfectly valid ways to write this equation. I used to be a stickler because we could take a triple, or I guess more like quadruple. I used to be like, oh, we could put a 4 there, a 26 there, a 16 there, and a 20 there. Still be balanced. Okay? So both of those. We'll talk more about fractional coefficients on Friday, but they're a thing. Okay, why you can have fractional coefficients. This is one example of an online equation balancer. I forgot I had this link in here. Told you my technology's not working very good. Yes, and you can't use this on a test. And I'm afraid if you use it for Alta, it just won't be pretty. So, like up here, I balanced like the decomposition of water. What you do is you put H2O, and you put the equal sign for the arrow, and you put the product. So H2 plus O2, and enter. Okay, and it balanced it. The green numbers are the stoichiometric coefficients. So if you really get stuck, you can do that, but you don't get it for a test. So I like it.
Does it show like the steps to it or?
No. So, no. Yeah, so let me know and go out there and do that doodle poll and see if there's a time that works for you guys or a time that works for you guys and me. And remember, I said the best time to study for any test, including a chemistry test, is not the night before. So I think I'm almost going to block that one out. We're not going to go the night before.
Are we going to receive the tests tomorrow? The results from the tests?
Yeah, I'll give you. It's in my office.
Oh, it's ready?
Yeah, it's ready.